Good day, ladies and gentlemen. This week I'm going to discuss with you constraint and unconstrained optimization using the boarded Hessian and the Hessian. I am Daniel Kabinetri 4 and I'm the instructor for this course, Applied Mathematics for Economics. Now, in this section, what we're going to learn is to be able to distinguish between concave and convex functions, understand what the Hessian determinant is, and also try to understand how this Hessian determinant is used to solve constraint optimization. And we also look at situations where we have unconstrained optimization, where the Lagrangian multiplier would be used. So in a GIGS, the outline is that we'll look at concave functions, unconstrained optimization using the Hessian, and then constrained optimization using the boarded Hessian. The textbooks are the same. Please go through them. All the topics are quite there. Now, what are concave and convex functions? I'll first look at it when you have a single variable function, which you have been dealing to date. Let's say y equals f of x, right? And if you have this function, or for a single variable function, f of x, it is concave or convex at a point x if in some region very close to that, very close to that point, the graph of that function lies completely below or into bracket above, in the case of convex, the tangent. So what you see over here is that you can see in this case the tangent is above and the graph is increasing here. Here the tangent is again above and then the graph is over here. What you see is that in this situation the graph is an increasing function. Here is a decreasing function. But then in both situations you can see that the tangent is above, the function itself. So we look at this one as a concave sort of function. The reverse is the case in the case of a convex function. What may happen is that we will have the tangent below, right? What we see here, right? You see there's a convex function. The tangent is below. There's an increasing function. That's why we have the first order differential equal greater than 0. This is decreasing function, and then the graph or the tangents is above the graphs. What we are discussing here is for a single variable function. But then we've been advancing, isn't it? We're looking at a function with two or more variables, right? If you take a function of this nature, I'm going to give you very specific examples. If you take a function of this nature, we are supposed to, investigate the concavity, convexity at a point. We differentiate it, slot in the point over here, and then the result is what you can see over here. Please look at this activity and try to understand what concave and convex functions are. Now, notice that we've been talking about, functions of multivariable functions. And if you want to investigate the concavity or convexity of multivariable functions, then we have to move a little further. And here, we use what we call the Hessian determinant, okay? The Hessian determinant. Now, what this determinant is that we just have to take the differentials of the function with respect to the first variable, the second order differentials, and then we have with respect to the second variable, here is what we have the cross partials. We put it in this determinant, and then we evaluate this determinant at the point where we are supposed to investigate the concavity or the convexity of that function. And these are the situations under which we will have a concave function or a convex function. I provide an example here. So this is our function. We take the first order, second order differentials. We find our Hessian determinant. And then over here, we evaluate at a point. And we see that we have a convex function. Please take your time and look at this example and then be able to get the tools on how to deal with concave and convex functions using the Hessian determinant. Now, recall that you discussed unconstrained optimization, using the Hessian. At level 200, you talked about maximizing profit, maximizing production, minimizing cost. These are all unconstrained sort of optimization. And if you do recall, there are three conditions for you to investigate the maximum or the minimum of a point, right? Now, the first order condition is that, the differentials, the first order differentials should be equal to 0. The second order, when you have these conditions being, satisfied, then you have more or less a relative maxima or relative minima in the situation when you have these conditions being applied. There is some other conditions which are, also investigated, like point of inflection, saddle points. For economists, saddle point of inflection, they are not very sort of interesting to us. Our main sort of discussion will focus on maximum and then minimum. Now, what we have, or the problem we have with this is that this is quite sufficient for us to discuss functions of two variables. So in a production function, when you have only two inputs, that is fine. But the question is that when you have more than two inputs, how do you go about it? And this is the value addition that we are going to make this section. Now, to be able to do that, we have to first specify the Hessian determinant, right? And formally, the Hessian determinant is a special determinant informed by arranging the second order partial derivatives in such a way that the second order direct partial derivatives are at the principal diagonal. So this is the second order partials. For a simple case, they are at the diagonals, as you can see over here. And then we have the cross second order partial derivatives at the other sides, okay? So for a simple function with two sort of inputs or two variables, we have the Hessian as defined here. And if we go back and look at this formula which we discussed over here, we can then have these conditions defined using the Hessian, as you can see here. The first order, there is no change. The second order, we have just expressed them nicely using the Hessian determinant. So you have to evaluate this matrix, the determinant. If it's less than 0, and then what you have, the alternating sign, then you're talking about, negatively defined, and therefore a maximum is attained. When they are all greater than 0, it means it is positively defined, and we are talking about relative minima. I have a simple example here. This example, you can go through yourself, you've done it. Just that here, you would be using the Hessian determinant. So I take my cross partials, I form my determinant, I try to evaluate at a point, and then I determine whether it's a maximum or minimum. Notice that once we know the maximum minimum point, we can find the maximum itself just by inserting the 2 points into the equation, and then we arrive at this solution. Where is the value addition? Assuming you have a function, a production function, that has got n sort of variables. Here, it means you have to find your Hessian determinant in this way. So you see the diagonal, you have the second order derivatives over here, and outside the diagonal, you have the second order cross partials in relative to all the other variables. So you have what we stand over here being the second order cross partials, what is stand over here being the second order cross partials, and then you have this condition. Now, once you have the second order, you have so I can call this one an n-dimensional sort of Hessian, because we have n sort of what? Inputs. Now, out of this, n-dimensional determinant or Hessian determinant, I can form what we call the principal minus. So if I take this one, this becomes the first principal minor, all right? And then if I take this one, assuming A3 or F13 were to be here, and I take this one, I get the second principal minus, and then it goes on until I have the last, the Hessian itself. What I'm trying to do is that I'm trying to define the conditions for a maximum or the conditions for a minimum when you have a function with more than two variables. So these are the conditions. So the second order conditions remain, the first order condition remains unchanged. The only thing is that the equality to 0 should be with respect to all the variables. And then we have this situation for the second order sort of condition, and the situation over here for the second order condition. notice that the matrices that you have here, they are the principal diagonals, okay? The principal diagonals, and here starting from 1, the principal diagonals which I defined over here. So this is the principal diagonal for 3, for 2, and then it goes on and it goes on. So you have to evaluate the principal diagonals at the maximum or the minimum points, and you see if the value is greater than 0, they alternate in sign, or if they are all what? Greater than 0, to know whether they are positively defined. And then you determine if it's a maximum or minimum. So the simple value addition with the Hessian is that it permits you to find the maximum or the minimum of any function with any number of variables, unlike a situation where you use the simple formula that you use at level 200. Now, this is an example. So I take, as usual, I take my first order derivatives, okay? I equate it to 0. And what happens is that, you know, we have to find for the critical point. So I have this 3 equations, 3 unknowns, linearly independent. The solution is unique. I solve for the solution. And here we have these solutions. The next point is that, so the solutions are what we have over here, right? X3, X2, and then the other one. Now, we find the second order derivatives, okay? So when we take the second order derivatives, we get this equation. So we have formed our Hessian, okay? And this is our H1, our H2, and this is our H3. The next point is to see the values of these H1, H2, and H3. And then you can see that in this situation, they have positive signs. So the Hessian here is said to be what? You know, a relative maximum, minimum, if you compare it to the situation that we have over here, right? So we have a situation where we have a minimum. And therefore, it means that this our point here is an actual, you know, sort of minimum, looking at the first order and the second order conditions. As usual, we can plug these values and find the actual value as we've seen over here, and the actual value gives us this. So what it means is that it is only at this point that we will get the minimum value. If we change any of these values of x, y, x1, x2, x3, we will get a value that is, you know, higher than what we have over here. There are some activities over here, of course, involving 3 variables. I would like you to take your time and go through them. Now, recall that we also solve situations where you are constrained, okay? In economics, we can have a situation where you are maximizing a production function subject to a cost constraint, minimizing a production function subject to a, you know, production quota, and here we use the Lagrangian. Earlier, if you know, so we have our Lagrangian, we form our Lagrangian. What do you know? We take the first order derivatives, and then, you know, we form, in this situation, we form what we call the bordered Hessian, okay? And the bordered Hessian in our simple case is what we have over here. Notice that in the case of a bordered Hessian, it is conventional to put a bar here, saying that this matrix that you see over there is a bordered, you know, sort of Hessian matrix. And you can see what happened is that if you take your full objective function, we take the second order derivatives, and then you put them here. There's the cross partials, and then the constraint function. We take the derivative with respect to x and with y, we put it over here, and then we have 0 over here. So this is how you form your bordered Hessian determinant in a situation where you have only 2 inputs. In certain cases, you can also form it this way, and I can hypothesize that the determinants you get here and the determinant you get here, they are the same. But I really prefer forming my bordered Hessian in this, you know, way. Now, recall that, again, for a simple 2 by 2 sort of function, this is the condition for a relative maximum and a relative what? Minimum. And in the same way, let's take an example and see how this will work out. In this small example, I have my function, I have my constraint function. All right, we are supposed to find the maximum and then estimate the maximum at the values. So what happened is that, as usual, we form our Lagrangian function. We take our first order derivative. We find the value of x, y in the Lagrangian. using, any method of solving simultaneous equation. And what happens is that if we go through, we have found our y to be equals to that 30, our x here to be equal to 40, and then there's our Lagrangian, which we can always do. So the next point is that we need to find our bordered Hessian determinant. So this is the second order, partial derivative. These are the cross derivatives. And we obtain this by differentiating the functions that we have here with respect to, again here, differentiating the Lagrangian with respect to x, with respect to y, and we get the values that we have over here. Now, the constraint function with respect to x is what, and with respect to y, give us this, and then we put the same values here, and then we have our bordered Hessian, determinant. So, trying to now evaluate our bordered Hessian determinant, we get this value. And therefore, when we try to put in these values, we have this equation. There is one thing that I think I have to tell you. Notice that in a situation where we have a function with two variables, okay, the bordered Hessian becomes a determinant, a three-dimensional determinant, even though we have given this one H2, right? It's the convention is that the value you put here depends on the number of variables that you have, variables of interest, and not on the number of variables that you are using in the equation. In this equation, the third variable is your lambda, right? But the real variables that we are interested in is x and y, all right? So we use H2 here. So if you see any a variable h with a bar 3, it means this matrix is going to be a 4 by 4 what? Matrix. Is going to be a 4 by 4 matrix. Now once we have this value over here, the value of x and y, we can plot it inside, and then we'll be able to know the actual, maximum or minimum. Here in this case we have a maximum, right, with the constraint that we have. So we form our, bordered Hessian, determinant here, and which we evaluate to be what we have over here. Now we have these two critical points, which we know is a maximum from the second order sort of conditions. We slot the values over here, and we are able to calculate. The maximum point. Now, where is the value addition? Now, with the help of the bordered Hessian determinant, you are able to find the minimum or the maximum of any constraint optimization. That is what is an optimization with a certain constraint. What you need to do is that you have to form your bordered Hessian determinant. Okay, so when we have an objective function of this nature, so here we have n inputs, and then we also have constraints function. We can usually form our bordered Hessian in this way. So these are the second order cross partials. This is the differential of the constraint function with respect to the variables, the first order, and our zero comes here. So the f is what I've defined over here. And we can also form in this way, as I told you, but really I prefer using what we have over here. Now, what happens is that if we denote what you have over here as the principal minus, recall I told you the principal minus is that we try to look at all the matrices in the middle, right? The matrices in the middle. So the first principal minor is what we have over here, and then it goes on to we have the n-dimensional principal minor. Then the conditions for a maximum or a minimum is what we have over here. All right. I must say that normally when you have a function of, let's say, 4 variables, and you want to solve this question, it takes a lot of time because, you have to do some mathematical calculations. So in many cases, when we have, more than 3 variables, you may want to use a software to do that. But with 3 variables, we can comfortably do that. So what is the value addition? The value addition is that the Bordered Hessian determinant permits you to comfortably, right, determine the maximum or the minimum of a function with any number of what? Variables. A more convenient way of doing that. And these are the conditions for a maximum and the conditions for a minimum. Thank you very much. I have an example here. Please try your hands on them, and let's meet at the chat room and then discuss how you were able to do this example.